special symposium on materials informatics. We have one more invited talk this afternoon, and then after that we have 2 more sessions by my colleagues and myself. So let me start by introducing our next speaker, Dr. Nongnut Adrit, and she is joining us from, I think, from the Netherlands here today, and from Utrecht University, a beautiful city which I have a chance to visit during the summer. And I have maybe about 3 pages of a long list of CV and accomplishment of Dr. Nong to go through, but let me just introduce her briefly. Dr. Nong Adrit, she's now a tenure track assistant professor in materials chemistry and catalysis group at the Dubai Institute of Nanomaterials Science at Utrecht University in the Netherlands. Before joining Utrecht University, she was a research scientist at the Department of Chemical Engineering at Columbia University in the US. And there she was also funded by the Center for Functional Nanomaterials at Brookhaven Lab. She is also a PI, principal investigator, in the Columbia Center for Computational Electrochemistry. So you know her background there, and she has obtained her PhD in theoretical chemistry from her University Bochum in Germany, and for the development of machine learning models for the application of in chemistry and material science. And she has a long list of career and accomplishment, and she's also the main developer of the open source atomic energy network. This is a package for the construction and application of machine learning models for material science. And her research interest lies a focus on the development and application of first principles and machine learning methods for the computational discovery of energy materials, and also for the interpretation of experimental observations. So I think I'll stop there, and without further ado, I'll let Dr. Nongnut Adrit begin, please.
Thanks so much, Dr. Apinya, for the very nice introduction, and also for the kind invitation to be here. I hope that everybody can hear me well, right?
Yes.
And
yes.
Also see my full share screen. So to be honest, it would be better if I could visit Thailand and also give a talk in person, and then we can have really long and real discussions. But unfortunately, that I think this is kind of like for the first time that we start to meet and discuss, and hopefully next time that we will get a chance to meet each other in person and have really the real discussion, and maybe we could plan for future collaborations. But anyways, my job today, I will just come here and sorry to say that it's a bit maybe too basic, that I'm going to talk about like an overview of the machine learning approach, and then we'll show a few examples of my own applications that we apply machine learning to for energy materials. And Dr. Apinya already mentioned that we also develop our own machine learning models, and also have our machine learning software package, for example, the atomic energy networks, which we develop the machine learning models, including the database. But I myself am a computational material scientist. The data that we develop based on the simulated data. If you don't hear me well, I feel like because from the previous speaker, maybe you can let me know if you cannot hear me well. I can also turn off my video and then focus on come close to the microphone later. But anyway, once we develop a database and also machine learning models, we also be ready to share with the scientific communities, and also opened, and also because we also reuse the data from publics too. So before I go to my slides or my talk, I would like to give the credits to the collaborators and also the facilities that I have been doing, and also some project that I will talk today that's based on the work that done when I was in the US. So I like to thank Professor Gabriel Saydas. So we developed machine learning models to understand battery materials. Dr. Jing Wang Chen, we also developed
can I just interrupt you quickly there? Have you already started sharing your screen? Because we don't see anything on the screen there. Have you started the slide already or not?
Oh yeah, I already, okay. Maybe I can stop sharing again. And
yes.
then I start to
Sorry.
share. So do you see my share screen now?
It's black and it said Nong Adrit has started. Oh, okay, here it is. We can see now. Yes,
Okay.
the first slide with your face on it. Thank you.
Okay, so then later I go back to.
Sorry, I thought you haven't started sharing. Thank you. Please continue. Sorry.
So yeah, basically that I will talk about give the overview of the machine learning approach and also some applications for the energy materials. And I like to thank a few of the collaborators that I have been working for a while already. So Professor Gabriel Saydas, that we develop machine learning models for battery materials, Dr. Jing Wang Shen's machine learning for catalyst systems, and also the discussion with the scientists at the Brookhaven Lab, Dr. Hybersons, and also collaboration with Dr. Ovans, Dr. Kirstner, and also April Cooper. As I already mentioned that we got support from Department of Energies and also support from Columbia Center for Computational Electrochemistry. So this is the work that I will be talking today. But again, I will really give overview only the beginnings is quite basics. That's why I would like to give the broader introduction. Sorry that many of people here already have seen these slides because I can see the audience, but maybe just for new people who are not familiar with this. So I myself, I am a computational material scientist, and we are looking at material properties. Is really for the modeling is depending on the properties, right? The length and also the time scales of doing simulations is really depending on the methods that you use, the accuracies, and also the physical properties that you are observed. So we use a wide range of methods. For example, the first principles calculations based on density functional theories or DFT. So we use, if we're looking at the material properties that describe very accurate electronics properties. So, but we can only look at the properties of materials, only a few hundred of atoms. But in realistics, right, we're looking at like a larger scale and including many different type of chemical species and like a nano scale and nano particles, like you can see here. So we apply or develop machine learning models to extract the accuracies of physical properties from the FT, and then we plug it in we develop machine learning models and then use it in applications for larger scales that we're looking at also the interface in nanostructures. And not only that, for even larger scales, if we want to get the physical property accurately, we need to looking at long time scale and also million of atoms. So we also developed the model with the like a Monte Carlo, like a cluster expansions, and also use in the finite temperatures with Monte Carlos, and then we do simulation with million of atoms. So the application that we look at, for example, looking at the computational catalysis for complex systems, especially the most important part and difficult part that we cannot address directly with the DFT or density functional theories is it at the interface. Like you can see the cartoons. If you see my mouse, you can see the cartoon here that contain a lot of chemical species and materials and also reaction mechanisms, right? So the material itself is already complicated with the surface model, with clusters, and also the reaction mechanism. For example, in this case, CO2 conversions to the green energies. There are so many different possibilities and also reaction that could occur. So we need to find, or we need to get the energy models or potential energy surface that can describe like a bond breaking and forming of the reaction mechanisms. And also the models that of materials can include different phases, gas phase, liquid, solid, and the interfaces. Sometimes it's also non-ideal surface like you can see here. And it's really very challenging with a few hundred atoms with DFT. That's why we develop machine learning models and then use it in the more efficient way, but still remain the accuracies as DFT. And not only the catalyst system, we also looking at the battery materials, because this is also one of the solution or to help to looking at alternatives energy materials, right? But then simulating or doing calculation of batteries is really very challenging for DFT calculations. And as you also know, again, this is the cartoon on the left-hand side. This is the example of the interface of the solid-state batteries. And also on the right-hand side, this is amorphous of the silicon anode. Once the battery cycling, you can see clearly that the material, like you can see on the left, with many layers, the cathode, the electrolyte interface, and also the anode of battery, the material after cycling is really become different, not crystal structures. And for the silicon anodes after battery cyclings also become like amorphous structures. So that's why to set up the models and do simulation, we focus on the nano size, the particles, and also in these regions of the domains. And especially the interface is very important to understand how it really interact between two types of materials, between the cathode sides and also the electrolytes, and also amorphous phases. That's why together with many scientists, we try to looking at by combine the atomistic simulation and machine learning, try to understand those type of the interface of catalyst materials and also the battery materials, right? So we are lucky that we got funding and support from the Gates foundations that to start to look at this type of fundamentals and also applications. So let's move back a little bit of the basics. I know that many of you already have seen and know about this already. Maybe just as an overview. So how can we use or apply machine learning in material science, right? As you know that machine learning can be just used as a tools or like the methods for data analysis, which is basically to help us like automate analytical modeling buildings or construct the models. So basically, what I said is that just machine learning we use as tool for data analysis. And then how we learn so we learn from the data. And then how to learn from data, we can do many things. For example, identify patterns and also to help to make decisions without using our own or human work or less human manual and working. And the data can come from both experimental measurements or even from my own expertise, computational modeling, because we can generate really cheaper and also in many different varieties of accuracy of the database to predict the physical properties of materials, like I mentioned before. So I think it's a lot of things that we should learn and start. I don't have really, in my opinion, I think these 3 textbooks are good for material scientists to learn the basics of machine learning, because there are so many different documents and books and new. I think this, if we start to understand those type of 3 textbooks, could already help to learn more applications and understand easily. So this is just a note you have record. Maybe you can take a look at this later. So basically, how can we use machine learning to accelerate, for example, modeling in materials science? So there are actually many ways, but I only pick 3 types of machine learning model that we can use to accelerate atomic scale or atomic simulation. This is my own expertise. Like you can see that first, we developed accurate and reliable quantum mechanics or based on first principles or density functional theory or DFT database, which is contain atomic structures, molecular systems, crystal structures in molecule or even interface. Sorry. The structures can contain also the properties, and for example, formation energies, elastic modular bandgap, or even spectroscopies, right? And then once we have a reliable and accurate database already, we can also use to construct potential energy surface, and then we get machine learning models to do efficient and accurate sampling simulation in Monte Carlo simulations or molecular dynamics simulations. Or we have the structures, and then we create machine learning models, and then we can predict material properties. Or when we have material properties, we can also do inverse design approach and then predict the unknown structures. So this can also use, and this is also very important for material science. So this is the outline of the principle of machine learning, right? Basically, the popular learning types and also their applications, there are so many. So I just make a list so that this is what currently many scientists they are using. There are supervised learnings, unsupervised learnings, and also sometimes semi-supervised learning or reinforcement learning. So there are so many different types of machine learning, but I will only focus on supervised learning and unsupervised learning today. And then second part, how we construct or what type of models and also model training. And also after we get the models, we have to validate, and then how to use it in the application in material science and show a few examples. So let's briefly looking at the basics, right? The first one is the supervised learning, like you can see here. So the supervised learning mean like we learn from labeled data. So for example, we have the pair of data X and Y, which we use it for training the models. X is the features, and then Y is the label. And the machine learning model we usually use to predict the labels, which is not seen or not for the unseen the data like the feature or X. So the typical applications that use in this type of supervised learning is it for classification or for regressions. Let's take a look the classification example. So we predict label of the new data points. So on the top here, the label data points, we use them to train. So you have the pairs, right, X and Y, and then we create and construct models. And now for the predictions of the decrease of the label of the new data points, like you can see here. So the reference data training, you can see in the feature X or the feature 1, we have X1, the feature 2, we have X2 here. We have the cross as class A, and then the square is class B, and then class C. And now when we start to predict the level of unseen, imagine that we have this type. So what we have is this show clearly that this is in the class C, right, that we have. And now the second example is the regressions. So usually we use the regression to estimate the relationships between like X and Y, and give, for example, the continuous function that related to independent variables X, like you can see, which is independent to the variables Y. So looking at the equation, maybe it's easier. So in the Y equal to this function that I have it here. Let's take a look what that is mean. So this is the dependent variables and regression models, and then we also have the independent variables, and then this is the model parameters, or W, sometimes we call also weight parameters. And most of the time that we also need to include, this is residual error. Sometimes we have to give the constant to shift to the right functional or the data that we have. So this already showed that machine learning provides the models and the methods for looking at or for find the model parameters by training, like you can see here. So the second one, unsupervised learning. So basically, we detect the structure in the data. Basically, we have a given actually only features, only X, but then no labels. And you can also see this type of applications, for example, for clusterings or dimensional reduction or reductions. So this is just a cartoon to show you. So only features used to train X, and then we create the models. And then for the predictions, we just have the origin data, and then we see what we can get it from the prediction, like Y. This is again the same type of reference data that we have. This is the feature X1 and X2, and then we train the model, but then we don't know what it means. And this is what we use. I don't know how to call is it trained or not, but suddenly we just clustered or use the method, apply the clustering, and then we see the group, like you can see cross, square, and also blue. So this is two types that many groups or many scientists use it for materials research. Now, looking at how we can really select or train and find the right models or for model trainings. It is not easy for me to also speak because it's really depending on your applications. So basically, the right choice of machine learning models really depending on the data, your database and data, and also the application that you have, right? So it's so difficult to speak. So the size of the data or the reference data set that you have. So for example, for the Google search that you are using to search and find things every day, it's billion of data points. But then looking at, we have for our materials, composition in material science, look at the periodic tables and what is it known or many is unknown, right? If you start to combine. So it's sometimes only hundreds of materials, composition and the properties. So the size of reference data set is really depending on your application and also what you are working on. And then the second point is the dimension of learning problem. So if you look at the dimension of a pixel in the photo, you have like a 1,600 times 800 pixels. But then when you have the experimental measurements, like the free energies in the lab, you just have temperature and pressure. I don't know how many data points that you can have. So is it really depending on your application and the data that you select? So there are so many different ways. And this is how I can comment. But then now also there are so many machine learning models that you can choose from, right? The supervised learnings or the technique that you can use it. There are so many, like the two excellent examples of the invited talks. You can see that we have also many things like decision trees and also ensemble of decision tree, support vector machines, artificial neural networks, or Gaussian process regressions, and so on. And then the unsupervised learning, they have a k-means clusterings or the t-snails. Then there are so many. This is a few examples and also references if you are interested in. It's really depending on your application that you can select to use the machine learning models. So now, next, I only have been working on only a few examples, but today I will discuss and show about neural networks and also some example of Gaussian process regressions. So let's take a look at the first example that how neural networks or machine learning models based on artificial neural networks. This is the idea that actually artificial networks are inspired by the biological neural network in our brain. So each neurons, like you can see here, is a nonlinear signal processors, and neurons take signals as input and then fire output when the signal strength in the very high or high enough. This means neurons apply a nonlinear iteration functions into the signals and then response as output. So artificial neurons also do the same. Like you can see here, now I convert that pictures to a simple feed-forward artificial neural network. You can either looking at the diagrams on the left-hand side or the equation that I show here. So basically, there are 3 layers. So the input layers, hidden layers, and output layers, and they all 3 layers are connected. Like you can see the black arrow here, they are the weight parameters and only go to the feed. So in our computational material science, we use input layers to describe atomic structures like bond angles or atomic distances. And then hidden layers is a machine learning model that you can use. In my case, I use artificial neural networks. And then the output, we get the energies. So we try to use a neural network to help to find the relationship between the energies and its structures, or structures and energies to get. And the derivative, we can also have like the forces, and then we can also use in the simulation, like a Monte Carlo simulation and MD simulation later. So there are so many different way to, or many, again, options to use for nonlinear, and there are so many different types. I just want to show as one example. This is the activation function that you can use it. It's a hyperbolic tangents, the sigmoid shapes or step functions, or ReLU and linear. There are so many, really depending on your database, how complex of your database, and how easy and how efficient of the algorithm and implementations. Let's take a look at a quick and simple, the nonlinear parabola that you would like to train and to see how neural network work. So on the left-hand side, this is the same diagram that I already showed before. This is input, this is a layer is X, and output layer is the energy, or the Y-axis here. And this is, we use one hidden layers and two nodes. Like you can see in the blue and the green, we apply activation function. Is it hyperbolic tangents? Like you can see the hyperbolic tangents for the very early, we see the blue curve and also the green curve for the second one. And then the combinations of the bias or the constants to shift the blue and the green nonlinear to the right parabola curve on the black diamond shape as a reference. And then we get the sum of all three terms in the red curve. So this is kind of like after a few iterations, it's get really the results of the neural networks predict the parabola is accurately, like you can see here. So this is also one information that we also need to consider, because there are so many different parameters how to tune. So in the communities, we call hyperparameter determines or assert and describe the model complexities. So basically the number of hidden layers and also the number of neurons per hidden layers, actually we have already to design or planned before training, but some people also implement like automatically search or screen many different type of hyperparameters and then start to fit and then waiting to see the results from the predictions. So they are, or these are hyperparameters of the neural networks or artificial neural networks. And then if artificial neural is really very complex, when we can also increase the number of layers or neurons, and also the more complex. This means the optimization parameter or the weight that I already explained before here in the black weight parameters. So we also need more. And then when we need more, it's also not always, you cannot always fix the number. You really have to see how the predictions is. It's really from your own applications, because of if you fit and you use too many hidden layers or too many nodes, it also can cause overfittings because of you have too many parameters. For example, in this case, the complex models really can be overfit. And you can look at the example of this curve or this graph. You have the x-axis and this is the cosine. You can see that the target training is in black, and also the training point is in white and empty. And you can see that if you look at the training points and target, fit really nicely, but the real potential is really not really accurate at all. This is showed overfit. So which is also not good, because your predictions is also, it's arbitrary. You cannot be trusted. Right. And then also sometimes machine learning model is also very poor for extrapolation. It means if your data not include or not similar to the training set, it's also difficult to trust. We have to be careful that maybe some region here not include in the training set. Maybe you predict something is not correct, not accurate. So this also have to be careful. It can show unphysics. And now the last part is this model validations. So we need to validate and to make sure that our model is ready to use or is good enough. Then we call model validations. So there are different ways to do this. So we split our data, or we prepare the data set for different parts. For example, in this case, we have the training set. So basically the data sampling that we use for training. And then we have the validation set. This is to use it to help to tune or to optimize the hyperparameters. And sometimes it's also to help to monitor if we have good progress in the training. And then the most important part is the independent test sets that we use to evaluate the performance of our predictions or error the estimations. So usually, again, it's depending on the data set that you have. Sometimes you use large trainings to optimize your parameters, and then to tune the hyperparameters. In the blue region here is some type of data set, and also the test set is to test and to make sure that your prediction is great. So typically, it's, the split ratio is depending on your data, how the size of your data. So if you have small data set, usually, I mean, this is just example. You don't need to stay like this. Like we split the training set 60%, the validation 20%, and the test is 20%. But if you have really very large and huge data set, then you can use most of the time that because you don't want to waste your database, like a 98% to train models and to get really the right and very accurate models. And then just use 1% to observe and to validate and to tune the hyperparameters, and another 1% to evaluate and to predict your the final model that you use. We call like independent test set. And many times that you get that problem of the overfittings. So we can also introduce some kind of algorithms to stop we used for example, we introduced the error, how to say, like we introduced some error stops because of it can also wasting CPU time and also not good because you might get also wrong models to use in your applications. And sometimes we also prevent overfittings by introduce the model like a regularization, and also to see if it is also to train longer, but it also still prevent the overfitting. But there are so many methods and many algorithms to help to prevent overfittings. And then now I will show a few examples of material science example. The first one is just a regression or example. So we use to develop potential energy surface. For example, here, there are so many different types of zinc oxide crystal structures. So we have the red is oxygen and the gray is zinc. There are so many different phases that you can see with the high energy structures and also lower or more stable crystal structures. So we collect the DFT database, for example, in isolates molecules or periodic structures and also surfaces, and then use it to train neural network potentials. And then we predict the crystal structures. As you can see that the DFT reference data in symbols and also neural network training in solid line. So all crystal structure or all phases of neural potentials predict in good agreement with the DFT reference data. And also another type of models, we have also complex copper gold alloy with the crystal structures. Here there are 3 types of the crystal structures of the copper gold. So the DFT reference data is show symbol and also neural network predictions after training in the solid line. So again, also after optimization and minimize the weight parameters, and then really minimize error, and then we also can get really the neural network potential predict DFT results accurate. And then just to recap the principle of machine learning that I just discussed with you before. Basically, machine learning can extract knowledge from information from data and also with less human work. And data can be labeled and also no need to label. And also many different types of learnings, like I show just really a few examples. There are many more and still really active in the field. There are so many different models that you can take a look. So, but I discussed today is mainly like a supervised and also unsupervised methods. And the choice of machine learning models is really depending on your data size, and also depending on your applications. So I discussed artificial neural network. I discussed how weights work, bias, also loss function, and also how to train. And then model complexities, how to get the hyperparameters, how to deal with overfittings, and also be careful about extrapolations. And validations or testing independent tests. Is it important to split your data set in 3 sets and also make sure that you have enough data and you can be confident on your machine learning models. So based on some example of my work, if I may continue, I think I have a few minutes to go. So we, as I already explained in the introductions, we develop our own machine learning models. For example, develop potential energy surface to construct really efficient and also accurate energies and forces that we can use it in realistic applications with the larger range and long time scales in Monte Carlo simulation and also in molecular dynamics simulations. So if you are interested in, you can look at a few references here that I list so that you can see details of our methods. So basically, we generate a database and then we select and analyze a database if it's really reliable and also accurate and also good enough for our applications. But most of the time, we don't have the complete reference data directly. We always to have initial data. And then we go to the second loop, by having the model selection or model training, and then we can start to validate, and then we can test the model if our application that we want to use is not good enough because the model that we have. Then we also include another feature or another features by use active learning to help, and then increasing database that we have. And then we do these iterative refinements until we get the right machine learning model that we want to use for our own applications. Maybe this is too abstract. I can show one example that we apply or how we construct our machine learning models. First, we have the initial data set. It's a few hundred data points or 1,000 data points, or it's depending on your ability that you can find the initial data set. So we then construct the preliminary results of the end potentials, and then we fit, and then we use it in application directly so that we can see that how far or the errors or good or bad our end potential directly that we have. In this case, we plug our end potentials in MD simulations, and then we predict the physical properties like the binding energies of the neural network predictions compared with the binding energies of the FT. In this case, we use example of water. So you can see for the first training for the first step, when you compare the DFT and the neural network, it's quite large errors that you can see. So this means we don't have enough or good data set yet to capture what that we really want, because of very high error. It also can predict quite arbitrary. Then we do iterative refinements by include the data that have high errors include in the training set. So we do this again and again, fit 1, fit 2, until it's really get as good as our applications that we needed. So again, we need to predict the physical properties, and many scientists may be confused that, okay, we already can looking at the root mean square errors of the fitting between neural network and DFT. So this is not the right property that we have to look. We should look at the really physical properties of the material that we want to observe. So basically, overall, we implemented these machine learning models in our open source atomic energy network. If you are interested in, this is the reference that I show. Let's take a look at a few examples that I apply our machine learning models for energy materials. So we're looking at many different types of materials. For example, the complex interfaces, amorphous phases, and also nanostructures. We're looking at two types of research directions. For example, understand and also find a way to understand the heterogeneous catalysis for energy conversions. For example, we look at the metal support interactions, solvent effects on the synthesis, and also help to find the active sites in complex oxide catalysts. And also looking at the complex battery materials like I showed before. Here are a few work that we develop machine learning models and also database. If you are interested in, I'm happy to discuss the model and also the database that show in this list, but I don't think that I will have time to talk or discuss all of the projects that we did, but I will pick a few of them. And not only that, we also support the ANET users. So there are so many groups also develop and apply and use our ANET. They also really share also, I think they also share their machine learning model, and maybe some group also share the database too, which is really very nice. This is the world of the open science, reuse and also reshare again. Okay, let's take a look at a few examples. The first example, so together with Professor Baylor, we also develop neural potentials to looking at like a very large scale realistics of the copper cluster at zinc oxide here. This is a good catalyst for methanol synthesis. So basically, I wanted to show that how we construct efficient and also accurate machine learning models to understand or to look at large realistic copper zinc oxide structure like this. As you can see that without a machine learning models, and we cannot do the FT calculation with such a large system like this. So you can see that we can also observe the phenomena and also the structures that can also looking similar to the experimental scales, right? And if after we get this model, we also checked the accuracies of physical properties, for example, energy and forces, and also compare with DFT reference data. And we also take a look at atomic structures together with our experimental collaborators. But I don't plan to discuss this in this presentation, but just want to show and demonstrate how efficient and also accurate of machine learning models to use it in material application. And then another example we have, this is use a machine learning model to looking at complex alloys. For example, the first one, copper gold for CO2 reductions, and also the second one, find the active size of the copper that sits in the sideral oxides, the application for CO oxidations. So this is the example that we work together with Professor Yang Xiaohuan at MIT. So they have really very nice experimental results from the UV with that. You can see that using only pure copper is oxidized too fast and also stay in the reactor is really short time. But then mixed with the gold composition with the copper, it lasts longer in the reactors. So it is very interesting if we can understand and we can help to minimize or even search and find the composition in the right position, how to say the right composition and percentage of copper or gold in the in this type of catalyst. But not only that, not only atomic structures, in this type of material is 5 to 10 nanometer cluster size, and also not only just in vacuum, it also in solution or in the catalytic conditions, like you can see here. So, and then as a computational material scientist, how can we help to identify the important compositions and also the surface structures? So we develop machine learning models and then have the DFT reference data, and then we construct many different types of nano particle size of copper and gold. We apply our N potentials and use it in Monte Carlo annealings and search for different type of compositions. So we let it run and also select only when it starts to equilibrium and different phases. And then we average the number or the concentration or the composition of the copper and gold in the structures, like you can see here. So in the structure in vacuum, you can see that the gold in the yellow like to stay in the surface, and the copper like to mix inside of the nanoparticles. So the larger you see that you can also see it rearrange and mix. It's really nice, like a core shell particles. But take a look at, if we looking at how efficient it is, of course, it's already our NN can give as accurate as the reference DFT data, but the CPU time to calculate one DFT calculations, for example, 147 atoms, it takes like 3 hours in the high performance computer or computing is 16 cores. But with our machine learning model neural potentials, with already after get the models, we can predict one composition of 147 atoms in like 1 second. And if we have larger, like a realistic structure like this, around 4,000 atoms, is with DFT, it's very difficult to find and also to really do simulation. But with our network, we take around 1 minute to get this energy and atomic structure like this. And not only that, when we do that application already, we can also combine Monte Carlo and also MD simulations to make sure that the structure that we found is really stable in different conditions. So you can see that at 300 Kelvin, and also 500 Kelvin, the structures still stay core shell like a gold on the shells and also copper in the core. And also many different compositions like you can see here, like the convex hull or the phase diagram. So we can really sampling so many different compositions with the help of machine learning models. And also at 100 or 1000 Kelvin, you can see that the copper gold nanoparticle starting to melt, which is also interesting to see. So not only that, we also include more realistic conditions that we also extend our database and also use it in water and solution. And then there are so many things that we can observe with the realistics. So this means the more complicated conditions, we can always include more data points and more chemical species in our database. And then we can also learn more. This is just to show example. Now, let's move to the next example. How can we help the experimental collaborators to find the copper sits in these structures? So Joseph Ilanis just came to me and asked like, oh no, I can see that you can find a copper gold structure rearranged in your nanoparticles. Here I have a copper serial oxides, but I don't know where my copper sits in these structures. Could you please help? So I said, okay, maybe we can construct the same machine learning models, but use different type of database. So we construct the machine learning models with the copper serial oxides, and then we start to use again the same method, Monte Carlos and simulated annealings. In this more Monte Carlo simulation that we use, the copper is in blue, the serial is in pink, and oxygen is in red. So you can see that we did long time and Monte Carlo simulations and then find where really copper sit in the structures. So at the end, after many different simulations, like a million steps of Monte Carlo simulation, and then we only take the equilibrate structures, and then we also find where copper sit in the structures. So most of the time that we see that the copper like to sit or like to stay near the surface, like our 100 surface or 111 surface, like you can see here after we collect the final structure from Monte Carlo simulations. And then once we see the structure like this, we can also take a look at the structure or the surfaces that we have. And then we can also look more careful, like a catalytic activities by do the DFT calculation again, and then looking at like the oxidation state of the copper. So we also see from our structure that we get from Monte Carlo simulation, we see like we have a lot of type of the copper oxidation state in the database, like copper 1+, 2+, 3+. So you can see here in our data. So if I may, I also have a few slides to show that we can also apply a machine learning models for catalyst discovery. So as you can see that in the past, and also a few examples from the previous invited talks already, that how to identify good catalysts that in the past that volcano plots, that the find the relationship between the binding energies and also the reaction rates of many materials. And then what is it on top? This is a good catalyst. And also another type of identify what good catalyst is also based on physics or physics-based descriptor, like a binding, like the Fermi levels or the band center, and then find the scaling correlation. But actually there are so many different types of descriptor to help to identify what could be good catalyst or not good catalyst. So the question is that, can we use machine learned or machine learned descriptor and then help to identify what could be good catalyst directly? So then let's see. So I think this is kind of like a good research question. So I decided to sit down and think, can we really do that? So I think I just use one example of ethanol reforming, use a catalyst as a metallic metal catalyst as example. So of course, myself, that I developed a large DFT database. But as I already mentioned before, it is not only DFT data. We need also to find way to validate and test our models. So we also collaborate and also make use of experimental data to help to validate and also learn from experimental measurement. But unfortunately, that experimental data is always very small number of data and also very expensive to create more. But anyway, let's take a look. Our proposal that we take a look. As I said, we use ethanol reforming for hydrogen productions as example, like you can see here, because it is also a future and green hydrogen energies. So you can see from the previous slides that actually we would like to get the hydrogen directly. So we would like to get these equations that we can really get a large amount of hydrogen productions. But in the same time, during or working on ethanol reforming, it is always happen that some reaction that we don't want or unwanted reaction could also occur. So it's also make the problem that it's also loss of hydrogens and also make the catalyst deactivate. So then what could be the right or the good parts? And we can have the right activities of the catalyst and also the selectivities to the hydrogen that we want. So this means we need to do some work. But as already known in the community, that predicting the activities is kind of like a well established by looking at D-band centers. Like you can see here on the left-hand side, we have the D-band centers and also we have activities. And then we can identify what could be a good catalyst because they have a low activation energy, is being the good catalyst. And also there are so many different type of reaction already. But then to predict the selectivities, it's really hard to predict because you have to know all of the reaction parts. So then this is kind of like a problem in the communities. So let's take a look at the data that we have from our experimental collaborators. So together with the Jingwang Chen group at Columbia University, so we found that the ethanol reformings that they use in the experiments, there are not many. So they use only 3 types, like titanium, iron, and nickel for this type of models. On the left-hand side, this is the tungsten metal. This is in purple and platinum in gray. And also another model is the platinum or monolayer on top, and also the cheap tungsten metals that they use titanium, iron, and nickel in these 2 models. So in total, they only have 7 data points and only looking at this. But then are there other tungsten metals work better or good or cheaper or work equally good than these 3 types of materials? So then we are start to do DFT screening to find activation energies of all parts. Basically, we look at bond breaking of the CC bond breaking and CO bond breaking. And this is just to show you some partial reaction networks. So the CO bond breaking is in orange, and the CC bond breaking is in blue. And there are so many different parts that could occur, right? And how can we really make use and see that, okay, which part? And we have so many different catalysts or materials that we have to screen. So if we sit down and do all kind of search, it will take a lot of time, of CPU time, even though it is not very expensive at doing experiments, but still take a lot of CPU time. So then I decided to name of the reactions as a label, and then we will see if we can make use of the machine learning models. So now we sit down and then think about the model. Can we train a machine learning model to predict activities and selectivities of this type of bimetallic catalyst for ethanol reforming? And as I already mentioned before, we have only 7 data points of experimental measurement, which is very small, and we have large DFT database. And so what can we do? So the first step, then we need to collect all of the NEB or the tangent state to find the activation energies. So we also use machine learning model to help to find the part to get, for example, in this example, is it like a C bond breaking of the ethanol? And I also show many different type of material. You can label anything, but then you need to really put the energies and also the activation energies, put it in the database that we have. So we use already the first step, use machine learning to help to accelerate the to find the tangent state of the calculations. We use the methods, not elastic bands or the NEB method, which should also make use of the Gaussian process regressions, the GPR models that developed by Jose and also Thomas Bligat at that time at Stanford, but now at the DTU. So if you are interested in this method, I also put the references here. So basically, we have to automatically search the activation energy for all parts. Like I just wanted to have, like I labeled before, from the reaction networks. And then we collect the features and also the target that we want to have. So we decided to have the two-step approach of two types of machine learning models, because we know that we can do calculations, the FT calculation with large NEB data to get the activation energy. So we apply the nonlinear models. And then the second one, how can we understand and predict the reforming activity and selectivities? Because we have to find the relationship of the experimental measurement. It's only 7 data points. So I decided to use linear models, like you can see here. So this is the physical properties that we collect in the data, and this is the target of the prediction that we want to have. And then we make use, and then we learn and get the information and use the linear models and also get the information from the prediction that we get from the FT. And then we predict the total activities, reforming activity, and the reforming selectivities, combination between the FT information and the experimental measurements. This is the prediction that we have. So far, we get, again, we're only looking at the 3D tangent metals in only the 3Ds in the periodic tables. So on the right-hand side, as you can see, this is the x-axis, this is the predicted reforming activities, and also the predicted reforming selectivity. And this is the best known already from the experimental measurement that they also show. But what we see here, we got a few more candidates that could also be good, but just sit down and look back. But why the experimental collaborator, they don't see this? Because of one parameter that we don't use or include it is that the stabilities of the catalysts, because it's also hard to predict in this case, because experimental collaborators also don't offer this. But anyway, even this type of feature that we use, it already can give us some idea that we can also get a good catalyst for ethanol reforming and predict activity and selectivities, and even propose new type of materials. And then we use the same model that we have and predict. And then I found that, okay, in this, we also can use different types of materials. But let's take a look at cheaper materials like molybdenum nitride, if it really works. So because I also found different type of material that we can see. And then I asked the collaborator from Jingwang Chen group at Columbia to check and validate by synthesis and also test the performance. And then you can see clearly that if they use just only molybdenum nitride, it's not active, not as good as just use other type of catalysts. So this is already show that using cheap molybdenum nitride materials is not working, not good as activities, and also cannot get any selectivity of hydrogen production that I want to have. But then using only pure platinum is also great selectivity, get a lot of the hydrogen production, but also not very good in the reforming activities. But then combination of this both that give both good reforming activities and also great reforming selectivities. So this is to show and prove that our machine learning models can help for material discovery and also material design, and can use cheaper materials. So our model also free and ready to share with the scientific communities. I don't think that I have more time to go, but I would like to just briefly show the conclusion. if you are interested in this work, I will be happy to discuss more, but maybe not today. We also apply other type of machine learning models to interpret the experimental measurements. But of course, I always doing on my side, because I'm a computational material scientist, I can generate a lot of simulated database, but nevertheless, we should always combine and compare our models with experimental measurement. So this is the new and the current project that we are working together with the current group that I'm here at Utrecht. And of course, just want to give one last comment here in the communities that actually is still a lot of challenge in the materials. I mean, the machine learning in material science, because of we really sometimes lack of uniform experimental data, and maybe if we have automations or robots can generate a lot of uniform data, this will also help. And so lack of the standard of exchange the models and data, because of many groups now start to do the same thing, it would be nice to share and exchange information. And also we need to find a better ways to understand or to combine data from experimental and also the computations. And I hope that I could show and demonstrate that training machine learning models on data from both experimental data and also simulated data can be useful for accelerating computational material discovery. And then I want to also mention that validate the predictions, or really make sure that you never trust your machine learning models. Always validate and validate and validate, either to compare with better or more accurate methods like a first principle database or even data or results, or compare your result with experimental measurements. And also the last part, that share data, it really help and support the communities that we can do more, and we don't need to prevent the.
Yes, hello. Oh. No. It said Zoom quit unexpectedly. It sort of crashed something. I would say here. Hello, sorry, there's maybe some technical issue there. I think, sorry, Dr. Nong, do you have anything more to say at the end there? Or there was just like just a brief technical hiccup at the end there? Sorry.
Oh, okay. Sorry, I didn't know that.
Yeah, it's okay.
So, okay. Oh, okay. So which which slide that you missed?
No. I mean, at the end, I think, did you, I think we've heard all the complete, I didn't miss anything, sorry. Thank you so much for your talk. It's very exciting to learn the applications that from your work, the research work that you have long been doing with your many colleagues in different institutes and universities in the US and also in Europe here. Thank you for going through the basic. I think it's not a waste of time. I think many of us here in the audience are just starting to learn about machine learning in material science domain. That's what I heard from many of our participants when we doing the registration. We asked them a few questions, and that's why we are here today, to learn new things. And maybe some of us has some experience in machine learning or AI tools, and that's I think we've also learned in different levels today from your talk. Thank you so much. And I think maybe we have one or two questions. May I ask my colleague, Dr. Samarkar, Dr. Nok here to conduct the question and answer, please?
There's a question in the chat box. Dr. Chakapan Alam Pongpan asks, does Dr. Nungnut develop the machine learning algorithm using Python or commercial software?
So actually our init code is the core is in front end, because it is very efficient, and also many software packages also use it. but we provide the libraries to share that can connect it with many other software packages that we have any libraries that can connect with Python or C or any other languages. So basically the main init core is in front-end because it is really efficient and also can evaluate really large data sets, millions or million of data points. We don't use Python as the core of the init, but we provide the init libraries that you can use it in many different applications with any other software package. So sorry that I skipped the implementation part. It's just to show very briefly, like a few seconds.
Thank you so much. May I ask you a question about the ANET, please? So
Yes.
I noticed there's a free code there. Is based on which coding language?
Of front-end language. Do you know the front-end? I'm sorry, I know that many young people, they don't know front-end anymore. So I'm old. Yes, that's correct. Yeah, it's front-end. Yeah. But again, actually, we are also trying to think now what type of programming language that we are going to use. We also think of like a JAX programming language, because this is, I heard that from Google, they also already demonstrate is it really efficient and also very easy to use. So we also look into this type of programming language, but I don't know JAX at all, but happy to learn with my students.
Thank you so much, Dr. Nongnut, for sharing the information with us. Thank you.
Thank you. So with that, I would like to ask everyone to help me to give a big round of applause to Dr. Nongnut for sharing with us and giving her time for us here today. Thank you, Dr. Nongnut. I'll see you again. Thank you. So I would like to move on to the next topics, which will be shared by two of my colleagues here at Master, and Dr. Tongchai Chukajon and Dr. Wanida Pongsak Sawat. They will share with us some of the ongoing work here at in our institute, and also maybe some of the planning for the future. Before we start, maybe I could give a few a brief introduction about two of our speakers, Dr. Tongchai and Dr. Wanida. They both graduated from the MIT at the Department of Material Science and Engineering, and since then they were with us. They've been with us at MTech, and then there's also at the RMT. Dr. Tongchai, she's a member of the research team, the research group in material processing and manufacturing automation, and her research team is the Smart Alloys and Manufacturing research team. For Dr. Wanida, she is now at the new center at the RMT, the Rail and Modern Transport Research Center, and in the team of the research team, it's called the Smart Manufacturing and Maintenance Technology Research Team. May I ask both of them to give us some information on the ongoing work and the future plans, please? Thank you.
Let me share my slide. Can you see the presentation, or is it the presenter's view? So let me swap the display. Okay, that's better. So my topic today is the current
sorry,
trend.
Dr. Tongchai, I don't think I see your slide on the screen here.
Oh, no?
No, it's sort of like black. Oh, okay.
I do.
It's okay now. Thank you.
Okay.
Okay, now please go ahead.
Okay, so as Dr. Epinya introduced us, my name is Tongchai Chukajon. I am a researcher at the National Metal and Materials Technology Center, or MTech. MTech is also a member of MASTA, which is one of the National Research Institute in Thailand. So the topic that I was given today is current trends in materials informatics for materials research at MTech. So I have quite a big shoe to fill. So I'll try my best. And if you have any addition to this, we can also discuss later, or you can also give us some feedback or suggestion later at the end. So as a materials research institute, like MTech, we are doing different kind of research and different kind of fields. But below, I am going to mention some of the broader fields of what we're doing. So the first one is material processing. So for the research that we do here, we have a lot of fundamental research as well as research that are translated or inclined toward industrial applications. So material processing mainly is focused on achieving certain targets. For example, can we have the best mechanical performance? Can we have the best functional properties of something? And sometimes it's not just achieving a certain target, but optimizing combination of properties. The second one of the material research area that we do is material testing or characterization. So we do testing of mechanical properties like tensile test, wear test, and other stuff, and also functional testing, for example, rheology and other things, depending on the application that we are aiming for. The third one is characterization of material structure. So here we can look into details the microstructures of each material or samples that we want to investigate, what kind of morphology they have, or the distribution of different elements within the workpiece or within the microstructure, because those things are going to affect the properties of the workpiece. And lastly, we have engineering research, and those are synthesis, optimization, and simulation of stuff or material or workpiece on larger scales. So, so we've come so far as a whole for materials research, right? So in the past, I think we have a lot of students here. So let me talk about the Edisonian approach. So I guess everyone here know Thomas Edison, right? And he was the inventor of incandescent light bulb, right? So when he was trying to discover the best material that can be used for the light bulb filament, he was using what we now call the Edisonian method, which is by trial and error. So that method was kind of inefficient and takes a lot of time and also incur a lot of cost. But it was possible and it was needed to be done at that time. But as we move along through a lot of scientific discovery, we can do a more systematic planning for experimental design. We can use statistical method like the Takushi design of experimental method to help with planning what kind of experiments or material parameters would be the best for achieving certain goals or certain combination of properties that we are looking for. And as you heard from the invited talks today, right now the current trends that could be really interesting for materials research is using materials informatics. So I have written here, I think, 4 of the interesting trends for materials research here. So first one is the optimization of material processing. So as a materials research workforce, I think we come across a lot of problems where we have to optimize multi-variable problems. For example, we can have a process that depends or use several factors like time, temperature, material composition, and so on. So those are examples of multi-variable optimization of processing parameters. And we optimize those factors to achieve multiple objectives. For example, it can be the improvement of not just a single property, but a combination of several properties, because improvement of a single properties is often not enough now. And to do those things. I think it is becoming more and more important to have data-driven experimental design, and it's also useful to have a, if possibly machine learning model or other models that could iteratively recommend the next experiment in order to lead to the optimization of your goal. So the second one of the trends would be the prediction of properties. So in the past, we might work with materials that are single component, but as we move to materials that are multi-component or are composed of different elements like the alloys materials, we have more variable like chemical composition to optimize for. And sorry, and sometimes we do not have the data for the strength or the hardness or the wear resistance and other properties of these multi-component materials. So those could be, material informatics could be useful for prediction of properties of multi-component materials. The second example is prediction of properties using something that is specific to the manufacturing rules and that make it difficult to find information or data in the current literature. And those would be volume fraction of secondary phases, porosity, and defects, depending on the process. And lastly, we can have different testing parameters that could affect the values or the magnitude of your properties. For example, during a wear test, you can have different volume loss at different loads and distance. And sometimes data on this kind of properties cannot be found in the literature. Another example is the tensile stress strain curve. If you apply different strain rates, you can have different behaviors of material. And third and the last example would be harnessing limited material data sets and also microstructure design. As a material research institute or workforce, I think we have tools or access to equipment that would give us data on material. For example, using characterization equipment like microscopy, spectroscopy, but sometimes those data are big, but there are a lot of noise to signal ratio. There's a lot of multiple factors that could be cleaned out. And if we can do that, we can achieve better prediction for microstructure design or phase formation. If we can achieve better or superior quality or cleaner data for material descriptors. So when we do have those things, I think it might be useful for solving multi-variable problems. For example, achieving a combination of high stress and high ductility, high strength and high ductility, and other things. And one of the necessary or steps to be taken is also having good material models for the problems that you're solving for, and also start thinking about data collection in order to use material informatics to help solve your problems. So I'm not sure, I think I'm on time, but so we can find out more information on MTech research on the website, www.mtech.or.th, and also look out for more training on materials informatics by the 2MI or Material Informatics project, which is being publicized right now. So those are the current trends that I found for MTech. So now I am going to pass the stage to Dr. Vanita for more current trends from RMT.
Thank you, Dr. Tong Jai. So let me share my screen. Okay. So in the next, hopefully less than 10 minutes, I'm gonna talk about the current trends in materials informatics and artificial intelligence at RMT. Okay, so So the materials informatics involved in our research center, RMT, is mostly based on the materials behavior after it has been put into use and throughout its lifetime. For example, the inspection data and maintenance, predictive maintenance. We also have some work based on the artificial intelligence, which I will introduce a little bit, but mostly the emphasis for today's talk is on the inspection and maintenance. So why is railway transport is important? If you look at this railway network map globally, we can notice that the dense railway network only localized in the world economics leader countries. It is because railway transportation is the most efficient and sustainable. It can carry high volume, it's a high volume transport that the amount of carbon dioxide emission is the lowest per passenger. And for Thailand, in this circle right here, we see that there is still more room for connecting the dots across the country and also as in our domestic domain, like connecting the major cities in Thailand, because that we gonna have more business development and technological growth. The major railway network in Thailand that goes nationwide is operated by the State Railway of Thailand, or SRT, for more than 100 years. So they go to the major city in 6 regions of the countries, and most of them right now are single track. In the near future and currently, some of the major lines are replaced with double tracks, and we have this high-speed railway plan going on that will hopefully be finished within the next 15 years, and we're gonna have major lines as a high-speed railway. Especially the most expected one is the 3 airport high-speed train that in the near future, you can take the high-speed train to Pattaya after landing at Bangkok. So with the growth of rail transportation in Thailand, NASDA, the National Science and Technology Research Development Agency, and MTech saw the opportunity and actually the need to drive the technology and innovation in rail and modern transport sector. So 3 years ago, we formed Rail and Modern Transport Research Center, or RMT. Right now, we have 2 research teams focusing on the smart manufacturing and maintenance technology, as well as the intelligent technology for mobility. If we look at the global trend in rail and modern transport, we will usually see this buzzword coming up related to AI, data-driven technology, artificial and sensor IoT database, big data analysis. These are the enabling tools for future advancement in the railway technology and actually in various fields in order to reduce costs of maintenance or reduce labor work. We see several startups starting to apply the AI technology to advance the railway industry. So I'm going to give some example here of some of the application of AI in railway and modern transport. The first one here, they use image data of railhead to capture the crack and classify them into based on the length of the crack. Then they couple that model with the crack growth analysis. With that, they can calculate the factor, we call risk factor, which indicates the risk of the crack growth when the train travels passing that location. And they found that the crack growth rate is higher when the train travel faster. So they can manage the speed of the train according to the defect, and also can plan preventive maintenance in time. So this is one example of using image and machine vision to observe the crack growth. Another example down here is the use of fiber optic sensor to monitor strain, stress, and displacement data on the railway asset as a structural health monitoring purpose. With all those data, they can use machine learning to analyze and classify the defect conditions. Another actual application that has been carried out and put into use is the use of drone by ProRail. I think it's from Netherlands. They equip this drone with the high resolution infrared camera in order to monitor the switching station in winter to make sure that the tracks at the switching station got heated properly, so reduce the accident in winter. And the last example here is the autonomous bus in China. In developing of the autonomous vehicle, it needs a lot of sensor and it needs the deep learning model in order to analyze the environment surrounding and tell the vehicle to go in the safe driving environment. So with all this current technology and our background expertise, our team now have touched upon using some AI and apply it to automated inspection, preventive maintenance, and autonomous driving. We are going to show 2 examples of the project related to automated inspection and predictive maintenance, because those are related to materials, which is the main topic for today. So this first project is the development of railway inspection by machine vision. The PI on NASDA side is Dr. Pitichon, and he teamed up with the AI expert at Mahidol University. The funding came from NASDA and the field tests were conducted at BEM. BEM is a train operator in Bangkok, and they usually take the time at night to inspect the fastener missing or defective parts by using human labor. Because missing fastener or defective fastener can lead to the derailment accident. But only the human labor alone, sometimes the work were not efficient enough, so they need some automated inspection device to conduct the work more efficiently and accurately. So this project takes the data in form of image and apply AI model to classify not just the missing or some defective, but it can also categorize into cracks, scratch, or corrosion. So this picture shows the prototype of the automated inspecting machine, which has been tested at the MRT underground line twice to collect data and to adjust the model. So the output from this project, actually, they found out that the prototype has done quite a good job that can identify the defect that hasn't been observed by human workforce. So the project has finished already within 2 years, which is quite impressive because of the strong collaboration with the AI expert. The second example is an ongoing project on on-site corrosion prediction of railway bridge materials by sensor data and machine learning. It's under CAST NASDA funding program. I am the PI on NASDA side, and Professor Tong from IMR is the PI from CAST team. So the problem came from that usually railway bridge in the past were made of steel and they were coated by paint. And usually the paint coating are not very protective in long term. So every maybe 15 years, we have to have a fully deep repainting of the structure. So it's costly, more costly. So the trend is to use weathering steel, which are alloying steel that form protective rust as we expose it into atmosphere. So this type of steel can be used without coating. So the idea of this project is to fabricate the sensor using the candidate materials of various weathering steel grades and collect the data from the sensor and the weather data in order to come up with the machine learning model to predict the corrosion behavior. So currently we have exposed this sensor in Thailand and China in order to collect data for 1 year. And after that, we're gonna perform the machine learning analysis on the data. So those are the two themes that we are going right now, the non-destructive inspection and the materials degradation prediction. If you find this topic interesting, I invite everyone to check out the recorded video of the symposium that we just organized on this website, and we welcome any further discussion and collaboration. Thank you.
Thank you there, Dr. Wanida and Dr. Tongchai, for sharing us some of the work that has been carried out here at NASTA, and maybe some of the future plan that you and your team of researchers and yes, have in mind to conduct in the future. And let me go on to the last topic which I would like to introduce to you as the training scheme. Let me share my screen here for the training of machine learning topics for the materials community here in Thailand. Let me share your screen first. Okay. Yes, I hope everyone can see my screen here. I will take a few minutes. I think we've already gone past our time, so I'll be brief. And I think many of us have already know about this scheme. So in order to, our team with multidisciplinary researchers here at MTech, and also some of our partners from Nanotech, and also some of the experts at the university at Chulalongkorn University, is that we are working together to develop a training scheme to help equip the materials research community with the AI tools. So the workforce development has been in the process for since last year, that we've started our effort in the preparing for the next generation, and also for the current workforce within the materials research community in Thailand, who might not have a prior experience in using AI tools or machine learning programming, or something like data analysis or data analytics to help process our materials information from our experiments or from the our research. So the three approach that we are working on to help create this skill, in order to, and we have a work together with our expert outside of material science field domains to design and the set up an appropriate course and course content that will suit our community, because you might find some other course on machine learning or deep learning that is like in general and may not be most appropriate for our research domain. And in order to do future research, we will take the second approach in order to support the adoption of the material informatics that has just started or in the process by the facilitate the adoptions of these new emerging fields to enhance the research here. And also our approach is also to engage other partnerships from local and international partners in this field. So I think maybe I can skip there. So the learning path that we have designed and have launched since I think the beginning of the week and has been receiving an overwhelming reception from many of the registrations that we have received. The first training course that we will do is for the fundamental knowledge and creating the skills in machine learning by giving some lecture and hands-on workshop on the course that we have divided into two tracks, track A and track B, and for the different purpose and different interests of the audience. And then afterwards, during the next steps, we'll have intensive training with short-term research work with the research questions that are suitable for machine learning approach, and with the suitable research question for the short-term, like 5-month research work in order to begin. And this will be carried out like next month, which is next week already, until next year, which is like the end of the project that we have been supported generously by the Ministry of Science here. So there are a few learning and teaching methodology that we will apply. We have like hands-on exercise and interactive lecture and workshop that we're planning at the beginning of the next year, and also the learning through the group learning that we can share some similar difficulties or some similar research questions for discussion. So I think many of us have already seen the details of the two tracks. Track A will be like, the format will be sort of like interactive, live lecture, 5 sessions in September on Mondays. And these sessions will be given by 2 our experts. One is Dr. Sira Sisawat. He's a researcher at the Faculty of Medicine at Chulalongkorn University, and he has a solid background in like computer science and mathematics, and he has worked with people with many different disciplines and scientists, working with scientists from diverse disciplines. So Dr. Sira has a very appropriate, very a good background that can help us to create this skill in machine learning, and also to create the fundamental understanding on the content of the data visualization and data management also that is necessary for machine learning models. And the other lecturer, the other instructor is Dr. Itti. I think maybe he's among our audience today. He's a researcher here at Nanotech at NASTA as well, and he has solid background in computer science and electrical engineering, and he knows a little bit, a lot about our domains in material science as well. So these 2 lecturers together with a team of teaching assistant will help, has helped us in creating appropriate course content and the design of the course, and also the workshops, the hands-on session, in order to help the participants of this course to create their new skills, or if someone has already learn something about machine learning and other associated tools, maybe they can brush up their skills and use it in the domains that they are working on in their research. So for track B is we have like about 11 sessions during spanning the 2 months in October and November and the beginning of December also. And we have a limited number of seats available for track B, but if anyone is interested and cannot join us for track B, like for the live sessions, the project will make recordings of the clips, and we'll have a platform available for you to look at these teaching clips and resource afterward in order to learn it at your own time and your own pace. So registration is still open, and we have the session date and time and there in the registration link. And also for the those who have already registered, we will inform you later about the online classroom, how to enter, and also some other important information. So if anyone be interested in, learning in your own time to create, or brush up your knowledge on or skills on Python programming and data visualization, our team of instructor has suggested maybe you could go into this platform on Kaggle, which is totally free, and there are many different courses, but for those for the fundamental understanding and maybe creating new skills, can sort of like choose this for mini course, Introduction to Programming, which is like 5 hours. In your own time, you can do that. Our Python for 5 hours and Pandas for 4 hours, and then data visualization for 4 hours. So maybe about in 20 hours in total. So I think that this will also be a requirement for those who are interested in entering learning with us in track B. Maybe during this time you would like to log into Kaggle and start learning these clips, or in this course here, mini course here on Kaggle. So I think that would be about what all that I would like to say about the first. Today, the symposium is the first event that we have launched for this project materials informatics project that has been led by our team here at MTech, and then the training scheme that is coming up in this 2 months, 3 months, and then in the early of the next year, we will launch the learning by the short research question during the 5 months of January until May. So we'll keep you posted, and for any upcoming information or any maybe an organized workshop that we'll be planning also during the next year. So thank you very much for your time. Let me stop sharing there. So I think as we have already used your time, maybe 15 minutes more of the plan, maybe if any one of the attendees would like to ask a further question or would like some more information, or ask our speakers to continue our discussion, I think one of the ways that maybe you could send us a message to 2mi, to an email at 2mi@mtech.th, and then we'll be sure to forward the comments or the question to the speakers or anyone here on the panels. So with that, I think without any other comments, I think I would like to thank all the speakers once again for preparing the very informative talks and the slides, and we have also got the slides, a copy of the PDF file for you to download maybe during the next 2 weeks we have that on the, I think we have already shared the link there that you can download on the Google platform. And so thank you. And thank you for all the attendees for joining us here today. And I hope you have, I wish you have a very pleasant evening. For those of you who are traveling home, please have a safe drive here at the Thailand Science Park, where our team are, conducting the symposium. It's been a lot of like thunders and rain. So safe travel, and I hope to see you again in the near future soon. Thank you very much. Goodbye.